Hi class, welcome to lesson 41 of Unit 6, Stoichiometry.
Today we're going to focus on the mole. We're going to define a mole and then convert between particles, mass, and volume and a mole. The first thing to remember is that a mole is a foundation of chemistry. Here are two practice Regents questions. When we see the word mole, we often freak out, as moles can be unpredictable furry animals or nasty looking hairy growths on our skin. But a mole in chemistry is everything. The mole has always been here. So let's look at these problems and see that if we remove the mole, we can still answer the question. The first question asks, what are the total number of moles of oxygen in 1 mole of dinitrogen trioxide? If you remove the word mole, you can still answer the question. Did you get 3?
Now you try the next question. Here we're looking for the total number of moles of atoms present in 1 mole of calcium phosphate. Just count up all the different atoms. Don't forget to distribute the 2 to the phosphorus and the oxygen. The mole is a keystone of chemistry and actually describes a specific number of particles. 6.02 times 10 to the 23rd, or what is more simply described as Avogadro's number of particles, as this was discovered by a scientist named Avogadro. Now, 6.02 times 10 to the 23 atoms sounds like a lot, but actually it's just the number of atoms that are present in 12 grams of carbon-12. So what 1 mole translates to is the mass in grams from the periodic table. If we have 6.02 times 10 to the 23 particles, we always have the same mass as that listed on the periodic table. Additionally, a mole could be 22.4 liters of any gas at STP. This is possible because the kinetic molecular theory states that gas particles have no actual volume. Please note that the mass of a mole can be described as atomic mass, gram formula mass, or gram molecular mass, or simply molecular mass.
So for every 1 mole, or 6.02 times 10 to the 23 copper atoms, you will have a mass of 63.5 grams, while when you have 1 mole of oxygen atoms, you have a mass of approximately 16 grams.
To find the mass of a mole, simply use your reference table. Always round to the tenths place. In this next example, you're asked to find the mass of a mole of calcium chloride. To find the mass of a compound, simply multiply the mass of each element by the number of times the element appears in the compound. So you can see here that when we carry out this mathematical operation, we get a gram formula mass of 111.1. Here is a diagram of 1 mole of very different elements from the periodic table. So you can see that elements have very different masses and very different sizes. Notice how the mole of copper takes up much less space than the mole of sulfur. But what we do know is when we have a mole, all of these containers contain 6.02 times 10 to the 23 particles. So all of these elements have very different masses, volumes, and therefore densities, but they have the same number of particles. We can use proportions to solve all mole problems, but the most common mole calculation is the calculation between grams and moles. You can find the formula to calculate between grams and moles here on the back of your reference table. Examining this formula, it's important to note that the gram formula mass is never x. It's the mass on the periodic table. In this question, we're looking for the number of moles. Here we know moles equals a given mass. We're given a mass of 100 divided by the gram formula mass of iron. On our reference table, you will note that the gram formula mass of iron is 55.8. Solve this problem and place your answer in the box to the right. In the next question, we are given moles. So we are given 5.75 moles of magnesium. We are not given a mass, so our given mass is X. We're going to refer to our reference table for the gram formula mass.
The gram formula mass found on the periodic table for magnesium is 24.3. So here we can cross multiply to solve for X. So what can be noted in this chart is whether or not you have an element or a compound. Whenever you have 1 mole of any substance, you end up with 6.02 times 10 to the 23 particles. So notice that in the nitrogen atoms, we have single atoms of nitrogen, but when we have nitrogen molecules and diatomic nitrogen, we call them molecules. So the label for the particle changes, but the actual number of particles, 6.02 times 10 to the 23, is always the number of particles that go with 1 mole of a substance.
Looking at this diagram, you can see that 1 mole is equal to 6.02 times 10 to the 23 atoms, the gram formula mass from the periodic table, or 22.4 liters. Now we can convert between a mole in any of these units by setting up a proportion.
Look at how we set up a proportion to compare the number of liters or molecules to a mole. Here we know that 1 mole is always equal to 22.4 liters of any gas at STP. So, if we wanted to figure out the number of liters in half a mole, we can set up a proportion. When we set up our proportion, we'll make sure that the numerator labels match and the denominator labels match. So you can see that we have our units matching. All we'll have to do is cross multiply. Once we cross multiply, you will notice that a half a mole is equal to half the number of liters, or 11.2 liters. We can use proportions if we increase the number of moles as well. So if we choose to double the number of moles, we'll set up the proportion. Notice how the units on the numerator and the units on the denominator will match. When we cross multiply, we can see that when we double the moles, we double the liters to 44.8.
In the first example, we're asked to determine how many liters of chlorine gas are in 4 moles of chlorine gas. Let's start with the mole map to identify our constants. We know that 1 mole is always equal to 22.4 liters. In this question, we are given 4 moles. So we'll want to make sure that our numerators match. Since I placed the mole on the numerator, I'm going to place the given number of moles, 4 moles, on the other numerator. And here I'm looking for how many liters. So this will be X liters. All we'll have to do is cross multiply and solve. Let's set up the next question together. Here, again, we have the relationship between moles and liters. So we'll start with our constant. We know that 1 mole is equal to 22.4 liters. But in this case, we are given 1.2 liters. And we're looking for how many moles. Solve this problem and place your answer in the box
So we know that 1 mole is always equal to 6.02 times 10 to the 23rd particles. So what will happen if we have half a mole? Then we should have half the number of particles. So notice how we can set up a proportion where we make sure we have the same unit on the numerator and the same unit on the denominator. If we have x and we cross multiply, we can see that 1 mole is equal to 3.01 times 10 to the 23rd particles. When we have the number of moles, we have the number of particles.
Let's work together to answer the next 2 questions. In the next question, we're asked to describe particles relative to a mole. So from our chart, we know that 1 mole is always equal to 6.02 times 10 to the 23rd particles. In the question, we were asked how many particles are in 4.9 moles. Again, we make sure that our numerator labels match, moles on the top, and our denominator labels match, particles on the bottom. Place this problem in your scientific calculator and choose the correct answer to the right. In the final example, we are looking for moles and we are given particles. So we have to set up the ratio between moles and particles. Again, 1 mole is 6.02 times 10 to the 23 particles. So notice when setting up our proportions, it is very important that we make sure that the labels of the numerator and the denominators both match. Solve this problem and select the best answer to the right. The idea of a mole was derived from Avogadro's principle, which states equal volumes of gas at the same temperature and pressure will always have the same number of particles. This is regardless of formula. We know that formula affects mass. Let's look at this Regents question. In this Regents question, we have 2 liters of methane gas and 2 liters of oxygen gas, and we were asked to find what is the same in both flasks at STP. We know it cannot be the number of atoms because methane's formula has 5 atoms, while oxygen's formula has 2 atoms. We also know the mass cannot be the same because methane has a carbon which weighs 12 grams and 4 hydrogens which weigh 1 gram each, while oxygen has 2 atoms that weigh 16 grams each. Since the mass cannot be the same and the volumes are the same, the density cannot be the same. So here, since these have the same volume at identical temperatures and pressures, they must have the same number of particles.
Can you use Avogadro's hypothesis to solve this Regents question? Hopefully you can. This concludes lesson number 41. Make sure you've taken good notes, you complete your homework on Google Classroom, and I'll see you in class. Good night.